Welcome to our code class for on-site energy systems. This is kind of a complement to another program that is NEC Fundamentals class that covers kind of the first 400 sections of sections 100 through 400 in National Electric Code. As a solar or battery designer, you might just skip right ahead to the solar specialty components. But if you take the time to understand the earlier sections of National Electric Code, the specialty rules and conditions turn out to be not so special after all. It makes it a little bit easier to not have to memorize everything, as if you take the time to learn the first parts of code, then you can understand better the second parts of code as the general rules are applied to specialty equipment. So National Electric Code follows a pattern. In the very beginning of code, they just outline very basic things, how power is brought on as a service, how power is distributed through the property as a feeder, what are the different kinds of cable and wiring and cable jackets, and then what's some rules just for general education. Well, now we're into later parts of code, specialty parts. At the very tail end of the general equipment section, we have a section on batteries, which is section 480. And even here, they're not, they're we have some new definitions people might be interested in. The battery cell, which they are defining as just the basic unit. That's not a huge. They're like, the battery cell is the atom. It's just the least commonly divided basic part. The smallest part of that battery. And let me know if my sound's going a little crazy, because I'm testing out a new microphone setting, and to me in my headset it just seems quite loud and like it's bouncing up and down. But if it's could just be my headset. So let me know if the audio feed it could be adjusted for your viewing pleasure. But anyway, the the cell is the basic electrical chemical unit of the batteries. And when we refer to a battery, we're referring to kind of the larger system. Electrolyte, they're not really trying to define or tell you what electrolyte is. They're just saying it's the liquid inside of the battery that allows the ions to transport. We have some new definitions: an intercell connector. And we have this connector definition, and you say a conductive bar or cable between adjacent cells. So wiring one cell to the next, that little piece, whether it be a metal plate or a conductor, that's called that specific wire is called the intercell connector. We have the terminals. And then terminals are the parts that you bolt your connectors onto that then stick down into the battery and become the cathode and the anode of the battery, the positive and negative side that's hanging out, and the electrolyte. So a little bit more definitions. Here's kind of an interesting informational note. The cell of lead acid versus the cell of lithium ion are fundamentally different for the same kind of amount of power, if you will. The lead acid has a native voltage of 2 volts, whereas the lithium ion has a native voltage of almost twice that. And so the way you stack up lithium ion batteries and lead acid batteries, you would get to a 48-volt battery system more quickly with a lithium ion system than you would with a lead acid system. And so, for the same amount of power, lithium ion is going to be a higher voltage and a lower amperage, whereas lead acid is going to be a lower voltage and a higher amperage. And generally speaking, the you want higher voltage and lower amperage. Higher voltage is cheaper than higher amperage. Higher amperage requires more metal for that current to flow through. And then another common kind of design mistake is when you are putting small lithium ion batteries, on a 48 volt battery inverter, you might find a super large, 12 kilowatt, 48 volt battery inverter, and it actually might be, if you only have a single string of batteries of lithium ion, the inverter might be oversized for the battery bank. So we talk about in our battery classes that a good rule of thumb for knowing battery sizing is know the standard discharge rates. Lead acid, like high-end industrial lead acid, is around you're doing pretty bad if you're at a 5 to 6 hour discharge rate, but anything less than that is just, you're going to generate more heat than power, and your battery is going to just drain immediately. So if you look at the inverter capacity with lead acid, you want at least 5 times that much in terms of kilowatt hour storage, just to be a bare minimum sized battery on a battery inverter. And with lithium ion, you're going to basically, it can withstand a little bit more, and that capacity is about 2 hours, 2 times the output capacity of the inverter. Anyway, we talk about that in the battery class. This is a code class. Let's just keep going. But just even in code, it says, hey, word up, lithium ion is a little bit different than lead acid. The cell itself, a little bit higher voltage, a little bit lower amperage. That means our basic battery equipment is actually changing, and this 48 volt standard that we have is really for, built around lead acid technology. Now we're getting into battery inverters that have higher voltages for battery banks, not just 90 volts or 75 volts, but a few hundred volts. You see storage batteries. Storage batteries and battery management equipment shall be listed. This requirement shall not apply to lead acid batteries. So there's been more kind of flexibility to experiment with lead acid batteries than other kinds of storage batteries in the past. Although, that's getting friendlier. The takeaway here is, if you're using building your own battery bank, let's say you're a hobbyist and you want to build a battery bank out of used electric vehicle lithium ion batteries, those batteries may not be listed for purpose for, putting them into a building. So you could fail inspection for that reason. It's not the case in international building code. You're allowed to do that. But I'd say, as a good rule of thumb, just keep in mind that if you are building a lithium ion project and you want to go into the low end of the price range of lithium ion by finding, and I found some really good deals on used lithium ion batteries. One was a utility scale project that had bought some LG Chem batteries and then decided to swap them out for a different battery technology. So we have used LG Chem batteries. Can we build our own battery banks? Well, the batteries that you use really need to be listed for purpose, and that's a little bit ambiguous, and that's also changing. At any rate, something to know about going into project permitting. Then we have a overcurrent. So do you need to put fuses or breakers on battery switches? Well, it says, it's different if it's a lower voltage battery and it's just being used to start up a generator, start up a motor. You can just wire the battery directly in and not worry about fusing that run. But that's different than a battery where you're using the battery for the energy kind of in a continuous fashion. And so a lot of the fusing and disconnect requirements we see for batteries come up in earlier sections of code. We have a disconnecting means for all ungrounded conductors derived from a stationary battery system. So some batteries, you will have the negative of the battery hardwired to ground. That gives it a 12 volt to ground reference. But really, the kind of more modern trend is to have the batteries be floating and not connect that negative side to ground. Well, if you have a floating battery bank instead of a traditional battery bank where the negative is connected to ground. And there's different reasons why to do this, but basically a floating battery bank has the negative and positive not connected to ground, and it's a little bit more isolated than negatively grounded systems. There's been blind spots in the ground fault detection of negatively grounded battery inverters and solar inverters that have resulted in fires, not because of the inverter, but because of poor workmanship on the rooftop, combining in a calamity of errors to sneak into the blind spot of a solar array. But there are blind spots to solar because the power and amperage can be very different on a overcast day or in the early morning than at high noon. So with solar, you will have opportunities where there's just a low amount of current or voltage that's less than what the fuses are rated for flowing through those circuits. And if that power is faulting to ground in a way that if the battery negative is not isolated from ground, it can create a blind spot in the ground fault detection. So anyway, if you say, I don't like the sound of any of that and I want to do a floating battery bank, you can. Your disconnect at that point will not just disconnect the positive side to the battery, but also the positive and the negative side. And then it needs to be a simultaneous disconnect. Since these circuits need overcurrent protection, it's not a bad idea to have it be a fused disconnect, at which point a fused knife switch disconnect can't go wrong with that. Although they can get costly at high amperage, they can get cost prohibitive at very high amperage. And so that's where your 48 volt whole house, incredibly high amperage batteries kind of fall apart. And maybe it would be better to have a distributed battery system. Anyway, those are design issues. But what this is saying is, just starting off the bat, you have to have a disconnect for all battery conductors for voltages that are, for ungrounded conductors, for voltages that are over 60 volts. You'll have to have disconnects anyway, but and you'll want disconnects anyway for if you're doing a 48 volt battery bank. If the disconnect is provided with remote controls and the remote controls are not within sight of the stationary battery, the disconnect shall be capable of being locked in the open position and field marked. So, if the service personnel on site needs to be able to open up that disconnect and lock it if you have, a relay system going on where you can press a button and turn the battery on and off. If that's the case, if you have remote controls on your battery, then you need to have a disconnect switch that can lock the battery in an open position. And that's what I like about National Electric Code is it's logical. This isn't just like made up rules thrown on the wall and see what sticks. You don't have to memorize all this stuff. You could, if you understand electrical safety, you can, reason out why these things exist and then not have to memorize it so hard. The disconnects on batteries are more flexible. We're not seeing, a knife switch disconnect, even though they're nice and robust, and that's what inspectors like to see. Legibly marked with the voltage and the short circuit current, and then the date that the short circuit current calculation was performed. I usually just, I haven't come across that. I generally just use the short circuit current on the spec sheet. So I guess this is a manufacturer provided test. Ventilation, to provide the room with a means of circulating air to remove excess heat, fumes, or vapors. There's really two different kinds of ventilation. One is continuous ventilation, and the other is just like an air conditioner, turning on and then turning off. So NEC will allow you to just have ventilation rather than continuous ventilation, whereas International Building Code wants you to have continuous ventilation. It's different nuances. 480, this should be 480.8 insulation of batteries. Batteries are heavy and they take up a lot of space. And so it's common to put them on a shelf. If you put them on a shelf, you need to check what the clearance requirements are of the batteries from the battery manufacturer. But batteries are heavy, so those shelves are often metal. So you're putting on battery on metal. Is that a good idea or not? You know, if you're picking up a battery with a lift it's a forklift battery, and you're wrapping chains around the battery and picking up the battery with a lift, you need to insulate the chains so that you're not, the chains are, getting down into the battery anodes and plates and causing a spark that could go up the chain and into the forklift and, electrocute the cab driver. So, you have to be careful with batteries. What about the shelf they sit on? Well, the support structure is usually metal for strength, or it could be the concrete floor and you're just sitting the batteries on the floor. But a concrete floor is considered conductive. If it gets wet, it can be conductive. If it's a slab, if it's a basement wall, or there's reasons that this concrete could conduct electricity. There's shelves that are painted and have anodized coating on it, and code is saying no, even that paint is not good enough insulation for batteries. What you have to do on your battery shelf is put down an insulated mat for the batteries to sit on between the shelf and the batteries. You're never going to move that mat. It's going to be there. But that's to prevent the batteries from charging the metal shelf, and that would be could be a safety hazard. All right, so there's airflow requirements that are part of fire code for batteries, and I don't think code does a good enough job referencing non NEC aspects of site safety, but I don't know. Common requirements. So live parts guarded against accidental contact for equipment operating at 50 volts up to 1,000 volts. They should be guarded from accidental contact, and the lead acid 48 volt battery banks will go above 50 volts. So I would call that include that. Nominal shall be guarded against accidental contact by any of these means. So putting the batteries in a room with a lock can be sufficient protection for the batteries, provided that room does not have additional, regular use. If it's a maintenance room, for maintenance personnel, versus just a storage closet that has other things going on in it. If it's just a storage closet with other storage, general pedestrian or even homeowner regular access, you would have to provide additional protection for the batteries so that only qualified personnel can touch those batteries. And so I had a off-grid project where we're putting the batteries in a external battery box, and the homeowner says, "Oh no, I want to make the battery box a room and do other things in it." I was like, well, okay, I guess. And we get to installing this box, and he looks at the battery and he says, "Well, can I electrocute myself if I touch those things?" And the answer is yes. He's like, "Well, how do I protect myself?" And it's like, "Well, we have this battery room, and you lock it, and you don't let anybody else inside of it." It's not a multi-purpose room. I've seen a lot of batteries just kind of, I'll put it in the closet in the garage. There's a difference between buying a completed battery, as we'll see in later sections, than there is in a hobbyist battery that you assemble. Anyway, to some extent, this is obvious stuff, although it does get overlooked. You could put a substantial partition between the battery and the rest of the room in that closet. And that's a common solution, to put like a metal cage between the battery and the rest of the room. Not a chain link wire fence that you can stick your fingers through. I'm talking about those like, oh wow, that's serious. A burglar wouldn't be able to saw through that thing kind of level of partitioning. Or you could raise the batteries by elevating it above the floor, by 8 feet. Although batteries are heavy, so that requires a good amount of structure. I like putting the batteries on the floor, on the concrete slab, on top of a rubber mat. That works pretty well. They make brackets for lithium-ion batteries to kind of stack alongside the wall. A battery location. So there should be a minimum clearance of 1 inch between the cell container and any wall. And then you also have to give consideration to if the battery is a unsealed battery that needs maintenance. You may need to back it away from the wall so that you can access that side of the battery for maintenance. So generally on a wall, you're mounting just the sealed type of battery, but kind of in our off-grid residential class, we talk about this requirement. We say if we have a wall and we want to put our battery bank along the wall, so here's your rectangular battery bank, and let's say these are lead acid and you want to maintain them. There's little cells that you have to stick your instrumentation into, and you can't access the backside of these cells. And so what a better way of positioning that battery is, instead of positioning the battery long ways, you position the battery so that the short end is against the wall, and that allows you access to those battery cells on all sides. So the battery can't be snug up against the wall. It has to be accessible if it is one of these kind of lead acid style battery banks. The terminals between the battery and the battery case or the battery shelf have clearance requirements per manufacturer specifications. And then there's what we'll see in later sections are exceptions to like this clearance space between the wall and the battery if it's not a assembled system, but it's a pre-engineered or kind of like a Tesla Powerwall, listed assembly of a one unit. Then you can just put it on the wall. So a few more requirements for kind of do-it-yourself batteries than just off-the-shelf listed full products. Doorways on the battery room should open such that a person could flee the room and the door would fling outward rather than inward. Gas piping is not allowed in dedicated battery rooms. And then illumination is required too. And so that was one where you might want to think about this too. Is your kind of illumination? I think that like LED battery powered click-on lights make pretty good things to go in a battery room that are independent power sources. You don't want there to be something going on with your battery inverter and you have to shut off the circuits of power and your lighting goes out. Now you can't see what you're working on. So there's ways to make this illumination and not complicate things, but more useful. And I had a battery bank that we built into kind of a awning on the outside of the house up against its foundation. And based on this kind of elevated concrete walkway, it's like, oh, well, we could stick the batteries in there. And, it really wasn't code compliant. The chamber was only about 5.5 feet tall. So I have to stoop a little bit when I'm in there, and it makes it much more difficult to work on the battery. Not only is it less safe, but it increases the time involved. And I'd say illumination is the same way. This was outside the house, and it's like, okay, well, they're not going to be working on the battery, and I'm just going to be here during business hours. And so we didn't put lights in this alcove. And then all of a sudden you can't see because the battery's in an enclosure. It's going to be in a room. That room needs to be illuminated. This is kind of fun. This probably should have been a little bit earlier, but there's a section for capacitors in National Electric Code, and it's only a page long. It's not very long at all. The one thing that is interesting about these, the deeper you get into code, the more code varies. So most electric code, when you're sizing the conductors, is you take the maximum short circuit rating of the device output, and then you multiply it by 25%, and that's your conductor ampacity before other kinds of temperature correction or whatever is applied. For capacitors, we get an additional ampacity. It's like, well, why is that? Well, capacitors are storage devices that can discharge their electricity very quickly, instantly, matter of minutes rather than hours. So they're faster responsive devices than batteries themselves. We don't use capacitors for home energy storage because they're substantially more expensive than even the most expensive lithium ion batteries. But they're saying if you're using a capacitor in a circuit for a very small amount of energy, but there's reasons to have voltage stabilization in certain equipment is one. And they say the output conductors of capacitors need to be sized more than 125%, because not only are these things, that 25% oversize is like, it's 100% of 100% of continuous load, 125% of non-continuous load. This is saying this is exceptional. This is even going to be powering devices not just on a less than 3 hour basis, but like a less than 1 minute basis. And so we need to make sure that fast rushes of electricity don't cause enough heat that it becomes burns up the conductor. So they have to oversize the conductor even more. And there's additional requirements for over 1,000 volts. So that actually got us kind of to the what we're gonna do is skip forward to the battery section that's in chapter 7 rather than the battery section that's in 480. So when batteries were smaller, they were in this section of 480. They've been added to their own section in the special conditions as well. And we're going to skip over the solar part and do that in the latter half of the program, which is section 690. So we're just going to jump ahead to chapter 7. And before we get to the battery section, which is 706, we have a few other things we need to review on our way to the battery section. The first is emergency systems versus standby systems. And the reason why I'm mentioning this in class is you have to be careful when you're designing and marketing, the capabilities of the battery system, and also listening to the customer to determine what they actually want. Because if you're calling, what you might call an emergency backup system, you can have electricity during an emergency. National Electric Code has a different opinion of what the definition of an emergency backup system is. You might have double redundancy built in. You might have rigid conduit instead of EMT conduit. Much more robust operating requirements for powering true emergency power systems on, in hospitals, for example. So what you would call, have power in the event of an emergency, might be a standby system. It's less critical, but even a standby system has, that's marketed as backup power or standby power, has additional code requirements than just a battery that's supplying a service panel. but you would, so I guess the question is, if you're trying to sell, a battery based system for someone who's going to live at home on, an oxygen machine, you there's a difference between designing a system to be compliant as an emergency system or even as a standby system, as opposed to just, oh, you have some backup electricity when the power goes out for your, you know home, for your air conditioning and refrigerators. So one of the main things for these systems is the transfer equipment needs to be capable of supplying the load. And that's like, well, why? I'm trying to avoid obvious things in these classes, and the fact that your power supply has to be large enough to supply the load seems obvious, but then you start looking at, most devices not using their full power rating, and then you start wanting to have backup power during an emergency, and you don't want to just have to pick and choose which devices to back up, because that requires rewiring your electric service panel, which is very expensive, $3,000 or more. But B, you don't want to have to pick and choose. I want my battery to power everything, not just one thing. Well, one of the reasons why that doesn't happen on these grid tied battery inverter systems, why they move towards critical load panels, is they can sometimes have like in the Solar Edge instance, the Solar Edge, it's a 7.6 kilowatt battery inverter, and it can export 7.6 kilowatts to the grid, but it only has a 2,000 watt, critical load panel, and you can only put, one or two devices on that, not even your whole air conditioning. And the reason is, like, if you're marketing it as a standby system, that supply has to back up your devices. And so that's why you don't get, a lot of jerry-rigged solutions where you wire up the critical load side of the inverter to a manual interlock switch on the top of the main service panel, and say, well, I'm just going to manage my electricity myself and not worry about critical load panels. The code says, your standby source needs to be capable of supplying the connected load. Maybe you're monitoring it, maybe you're implementing load control, but you can't have a standby system that is unstable, because it can only output 4 kilowatts of power, but you have so many devices on it that you would regularly exceed that capability and turn your power off. That by itself, that kind of design flaw issue of just you're having poor electrical performance is against National Electric Code for standby systems. So if you are trying to pass inspection with a design, and your inspector is like, well, is this enough backup power for this backup power system? You could fail if the inspector determines that it's too undersized for what kind of transfer switch application you're trying to do. All right, so then we get into section 705. 706 is the battery section. We're just marching through chapter 700. Second half of class is going to be on solar code. But here in section 705, we get to the rules that govern interconnected electrical systems. So the rules that are like, well, can you land on the, as a supply side interconnection versus a load side interconnection? Can you connect to the breakers, or do you have to do a standalone service for the solar array? All those rules can be found in section 705.12, which is actually after the solar equipment section. On the supply side, it says quite simply, the sum ratings of all the overcurrent devices connected to the power sources shall not exceed the rating of the service. What that means is, if I have a 200 amp electric service, I can put up to a 200 amp backup power system or transfer switch system or grid interconnected solar array, whatever kind of system it is. If this is a 200 amp service, what that means is that these conductors going into the service are rated for 200 amps. And if you want to tap onto these conductors as a supply side interconnection, you have the ability to do a system that's as large as 200 amps. So that if all of the solar power was being pulled into that main breaker, and you could use that full panel rating. Most homes are only operating at 3 to 8 amps on a given minute. And when electric tank water heaters pop on and other things turn on, you can get up to 40 or 50 amps. Electric service panels rated for 200 amps, so you could do quite a large 50 kilowatt or just under 50 kilowatt between your solar inverter and your battery inverter all tied in there. But the sum total, if you had a 50 kilowatt solar array and a 50 kilowatt battery inverter that were AC coupled, that would be overpowered for a 200 amp service. You can sneak in additional power on site. If you just had a 200 amp service and you needed a 400 amp service, you could have a 200 amp system as a supply side connection, and then have at least a 40 amp plugged into the load side. Or you could just start doing a series of cascaded service panels and then just be plugging in one-way grid assist inverters go in that direction. So you can, if you need more than 200 amps of power on a property, that doesn't mean you need 400 amp electric service anymore. I don't like 400 amp electric services because the disconnects, the transfer switches, all get much more complicated. You're often dealing with actually two 200 amp service panels, and that 400 amp service only gets combined at the meter base. And so, isolating those switches and doing automatic transferring, just gets way more complicated. We have the definition of a grid interactive system, an electric power production system operating in parallel and capable of delivering energy to a primary power source. Okay, the grid tied system is a grid interactive system. Now here we get to the load side of the interconnection. So there's the supply side where you're coming into the utility feeders, and then there's this load side. Now, the load side is when you have an electric service panel and instead of going into the utility side of the main breaker, supply side, we come in between the meter and the main breaker. Here are all our breaker slots. On the load side, we go into the service panel itself. And so I guess the question is, can we just go into anywhere on the service panel, or do we have to go at the bottom of the bus bar? It says, well, if we go in anywhere, anywhere in that electric service panel, if we just go in wherever we want, you take the 125% of the output rating of the inverter. So that's that 125% oversize. And normally at that point, you would round up to the nearest breaker size. So on a 16 amp in-phase microinverter circuit, you do a 25% over current protection. That gets you about to 19 amps or so. You round up and you put it on a 20 amp breaker. And so it used to be called at any rate, whether or not you're calculating the output of the inverter times 125% or just looking at the breaker that the inverter is tied into, they're very close together. Not far apart. So it says the output of the inverter at its breaker rating, or maybe technically just slightly less than that, you know, plus plus the rating of the overcurrent protection device protecting the bus bar. What is that device? That is the main breaker. No, I think I chopped that out. No, this is it's plus the rating of all the overcurrent protection devices protecting the bus bar shall not exceed 100% of the ampacity of the bus bar. So what I butchered in trying to explain is that if you just go anywhere on the service panel, then all of the breakers on that service panel cannot be more than 100% of the main breaker rating, or more than 100% of technically what the service panel bus bar, this piece of metal that's connected to the utility conductors that all the breakers are connected to. This piece of metal has an amperage rating. And if you just connect the solar array anywhere on that service panel that you want to, that amperage rating cannot exceed 100% of its rating. So you count up all of the breakers and say, okay, well, if we had 50 amps of this and 20 amps of that and 10 amps of that, that cannot exceed the 200 amp rating of the service panel, more specifically the bus bar. Some service panels, not many, some have bus bars that are rated slightly more than the panel itself. It's the exception to the rule. Or if you locate the solar array at the very bottom of the bus bar, at the opposite ends of the bus bar, then so the solar array comes in the bottom, the utility conductor comes into the top. Really, there's 220 volt bus bars, and they split the breakers. Well, if you come into the top of the bus bar with the utility feed and the bottom of the bus bar with the solar array feed, then National Electric Code says, well, those power supplies are divided so that by the time you get to the middle, the current has already gone into the devices, and you don't get that, overloading of the bus bar ever, as long as you stay within reason. Not overloading the bus bar by 150%, but they're flexible. They give you 20% extra bus bar capacity. So on a 200 amp service, you could have 200 amps from the utility and 40 amps of solar, because and put that all on a 200 amp panel. So you'd have 240 amps of power going into the panel on a 200 amp rated panel, but it's not a safety hazard because the solar array and the grid are located on opposite ends of the bus bar. If you don't do that, if you don't divide it up all that way, then what would happen is you could have all of the power coming from the utility going into the bus bar and all of the power from the solar array going into the bus bar. And so at that specific point, you could have a 240 amps of power supplying a bus bar that's rated for 200 amps, and that bus bar heats up and it burns the building down. And so the way you prevent that is to say, well, if you're going in all willy-nilly on whatever breaker slots you want, then all of those breakers cannot add up to be more than 200 amps. So you have 50 amp of solar, 50 amp of solar, 50 amp of solar, 50 amp of solar, and now it's on a 200 amp distribution panel. That's actually quite easy to do when it comes down to it. The only complication is, if you have 200 amps of power supply feeding a service panel, you have to have this extra capacity to tack solar in on the other side. And if you put too much solar on the other side, then you're overloading the panel. So, there's a specific circumstance where you're allowed to connect 20% more ampacity than what the service panel is rated for. And that's when the two sources of power are located at opposite ends of the bus bar rating. So I think I'm just restating this. And then when you do that, so this is a duplicate slide, but the only new information here is that when you do that, you have to put stickers on that breaker that's down at the bottom of the bus bar. If you're choosing this special election, then there's an additional label that you have to put on the service panel that says don't change the position of this breaker because it has to go here. Otherwise, if you relocate it somewhere else on this breaker, it could be a safety hazard. So, when you elect the 120% rule, you have to visually indicate that on site. And so, like, the ways like inspectors approach these projects is they might not know all these rules, but they might have heard about this special rule, and they open up the panel and they say, okay, well, if the breaker must be at the bottom of the bus bar, you need to indicate to someone else down the road that's the case. And they might not even know that the label requirement is actually spelled out in code. They just understand that code is going to make you label these, especially when things are special exceptions, to indicate as such. So similarly, if you don't do the special election, if you put solar, if you put 50 amps of solar and then a 40 amp water pump and then a 10 amp exterior lighting and then a 20 amp solar battery inverter, and you sum it all up and it's not more than 200 amps, so you put it all together on a 200 amp service panel. If you do that, you have to put a sticker that says, hey, make sure that all the breakers on this panel do not exceed the ampacity of the bus bar, because that would be a safety hazard. Two different cases, two different stickers. And finally, we got, this was added in 2017, resolution about center-fed panels, where instead of having the main breaker at the top or the bottom, you now have it in the center, and the bus bar kind of feeds out that way. It says, well, you can still use the 120% rule, but you can only connect that at one end and not both ends. For that matter, you could do some load stacking. You'd want to put, breakers, your heavy load devices up here, maybe your heavy always on loads up there too, to be, I don't know, stylish with your electrical load distribution. All right, so equipment containing overcurrent protection devices must indicate the presence of all the different power sources that are inside that equipment. And so now we get to, again, right now we're just in interconnected power systems. So this is solar, this is batteries, this is anything that's interconnected to the grid. We finally get to this disconnect device, and it says it needs to be readily accessible. That's been changed in 2020 to be outside the building. Externally operable without exposure to live parts. So you might, for some reason, put a disconnect switch inside of a box. So you have to open up the box lid to flick the switch. This says no, this is an externally operable switch that you should be able to operate without exposure to live parts. It needs to plainly indicate whether the device is open or shut. So sometimes in cheaper battery kind of do-it-yourself world projects, you get little turn knobs, like in a boat marina. You have this knob that has a dial on it, and you turn it to open it clockwise and to close it counterclockwise. Well, that doesn't indicate whether or not the switch is in an open or shut position, and so that would even if it's a listed disconnect for the voltage and amperage, that's not suitable as this battery disconnect, or as an interconnected energy system disconnect. It needs interconnected energy system disconnects should indicate whether or not they're open or closed plainly. When if the system is capable of powering the load side of the disconnect switch. So what they're saying is, like, on disconnect switches, you have terminals for your wires at the top, you have terminal wires at the bottom, and the power supply, the utility side, the supply of the disconnect comes into the top, and the load, the air conditioning unit, the load side of the disconnect goes into the bottom. But on a certain device, like if there's a solar inverter here, you still have the grid side coming into the top, but you have the solar inverter side coming into the bottom. If you're capable of energizing these bottom loads this direction, you need to indicate that. Now, I could argue, I hope the lawn sounds aren't too bad. It'll pass. But I could argue to an inspector, that the solar inverter is not capable of operation when the grid is down per its listing, and get out of that sticker that says the line and load terminals are energized the open position. That is one of the more poorly enforced codes, is you're putting stickers on units that say the terminals in the load side could be energized when they can't be. But if this were a battery inverter that had its own storage and didn't turn off and is capable of backfeeding the grid, then you can say, hey, you need to be careful. This system is capable of backfeeding the grid even if this disconnect is turned off. And that means the system could be backfeeding the disconnect. So you have the disconnect switch turned off, you have the lid open, and in actuality, all you've disconnected is the switch part. You still have an energized top and an energized bottom. You would have to have a different disconnect somewhere else to kind of isolate what's ever in between, so that you can service what's in between. So if you have the possibility where both sides of the disconnect switch can be energized while the box is open, you need to say so, on a sticker. If that's not the case, then you don't need to say so. Now, here's another thing, is the simultaneous opening of all ungrounded conductors of the circuit. And so, again, if you have a battery inverter and only one of the circuits is ungrounded, you get into this disconnect switch that's a turn knob, and it'll isolate that one circuit. But now, if we have two ungrounded conductors, a positive and a negative, that are floating, AC conductors, where you have a 120 240 split phase and you have two legs of 120, the disconnect switches need to disconnect all ungrounded conductors at the same time. So you can get breaker switches that are like triple gang breaker switches that have a bar that turns off all the disconnect switches at the same time. So there's like 3 disconnect switches built into here, but there's a bar that connects all of them together. Or like a knife switch disconnect, where you have the different isolated wires going into the middle, and you can pull the lever and it disconnects all at the same time. What you don't have is like a separate disconnect for leg 1 and a separate disconnect for leg 2 that you turn at separate times, so that you could get into an imbalanced load or something like that. So, that's kind of the hard part of wanting to build your own battery boxes to avoid the high cost of battery specialty parts, is getting that simultaneous disconnect. You have to give yourself a substantial balance of system equipment budget for battery systems in particular, to get all the overcurrent protection, all the disconnects for servicing. At which point, Tesla, their only downside is lack of availability, which is a huge downside. It's can be some accuse them of being snake oil salesmen because you can't, always get access to the products that they're selling at a price point that has people wait in line for a long time rather than actually move forward with their projects based on what's really capable of being delivered at scale today. Anyway, um, can be a good business model for them, I guess. Location of the overcurrent protection device for supply side connections. You always need to have this, the main breaker, the main fuse, the main overcurrent protection device for the system should be within 10 feet of the electric service itself. So sometimes if the array or the battery system is far away from the point of interconnection, you might have to have a disconnect switch on both sides of that cable run. But by default, you need to have a disconnect within 10 feet of where the utility service enters the property, where you're making that point of interconnection to the utility service. So, like if you have, let's say you have the line side tap is over here, and then your solar array is in a field over here. The question becomes, well, I need a disconnect switch. Do I put it over at the solar array, or do I put it at the utility point of interconnection? You have to put it by the utility point of interconnection, and then based on line of sight, 50 feet line of sight, anything more than that, you might then need a disconnect on the other side too. At which point the disconnect switch that's by the utility disconnect needs to be a lockable disconnect switch. So someone can pull up to that electric service and see that the power has been turned off and is locked out and doesn't have to go hunting around to know it. Loss of primary source, loss of three-phase primary source. This is basically saying that, hey, if you have a grid-tied inverter and it loses power, it needs to turn off. What's interesting about the loss of three-phase primary source, it says, well, actually, if you have a three-phase inverter that is designed to also provide backup power to the electric grid itself, it doesn't have to turn off. So we're going to give you a kind of direction to say, look, this isn't always the case, and utilities are still trying to understand and drive better products to market so that they can take advantage of distributed power resources, say during a grid outage, so that they can power one portion of the grid while they're working on the wires of a separate section of the grid. Almost to our break. So let's see. Still with interconnected power, we have the way you size your conductors. You take the inverter input and output rating, and then you mark it up by 25%, just a standard oversize. And then it says, well, you don't actually need to mark it up by 25% if you're using additional circuit protection somewhere along the line. And so where that occurs in solar is like if you're using inline DC optimizers or microinverters, then you could use 100% of the output rating and not 125%. We're going to see this come back in the solar section. It's going to make a little more sense at that point. It says circuits connected to more than one source should have overcurrent protection. May not be required for circuits using 125% of the additional oversize if there are no external parallel power circuits. So what this is saying, we see this said in code in a couple of different ways, but basically if you just have a single circuit, and so you have the solar array here, and then one circuit going back to the inverter, and that's it. that's a little bit different than if you have two circuits that can then get wired together. Basically the rule is whenever you have multiple power sources, when you have two solar arrays coming into one point rather than just one, you have to be aware that the solar array could start backfeeding the other circuit. And so what this is saying is if you just have one source, one circuit, you may not need to have an overcurrent protection device if you can prove that you've oversized the cable and beyond the short circuit rating of the device, and that's all the current that's going through it, then you could get away with a disconnect switch and not an overcurrent protection device. But any other circumstance, in this point where multiple circuits, multiple power services are combined, whether that's a service panel or a combiner box or whatever, when you have multiple power supplies feeding one bus bar, then you with that, and there's rare special occasions where this is not the case, such as supply side taps made within 10 feet of the point of interconnection. But this is not supply side taps made within 10 feet. This is where you have multiple solar arrays feeding one combined point together. It says circuits where you have more than one combined point need to have overcurrent protection built into the circuit. If you only have one circuit by itself, it may not need overcurrent protection. But if you have multiple circuits somewhere in that circuit, whether it's over on the inverter end or done at the combination itself, like in a service panel, somewhere along there, you're going to have overcurrent protection to, prevent the circuits from backfeeding, or in the event of a backfeed, that the circuits will blow rather than continue to push the electricity further down the line. Okay, so inverters need to have AC and DC disconnects that may be in addition to the readily accessible disconnect on the exterior of the building for fire departments. Now, often these inverters will now have disconnects built into the package of the inverter, even if it might be in a separate location on the inverter than the rest of the inverter. And there needs to be a plaque on site that indicates when you have an inverter that's not, right by the service and readily accessible disconnect, you have a plaque that indicates the other disconnect locations. The neutral conductor sizing, without getting into too many details, I'd just like to say there's special considerations for the neutral conductor sizing for 240 volt inverters on three-phase power systems, where they're using two phases of the three-phase system. And then additionally, if the equipment ground conductor, if the neutral is only being used for communication. So on a solar array inverter system that's a perfectly balanced system, it outputs the same amount of power on leg 1 as leg 2. It doesn't need that neutral. It may just be using the neutral for communication. And so it says, well, if you're only using the neutral for communication, you can size it to be the size of the equipment ground conductor, which is much smaller. So now we're back. We're at the end of 705, and we're going into 706, which is another battery system. And it says this applies to all batteries that operate at over 50 volts AC or 60 volts DC that may be standalone or interactive with other power production sources. So they're saying, look, this is the section we're going to be putting our future, large, building tight battery code requirements into. There might be other reasons to use batteries elsewhere for other things. This is going to be our building, batteries for building section. And we have more vocabulary terms. It doesn't really try and tell you what a flow battery is. It just says it's similar to a fuel cell. That's how I explain it too, because pragmatically, there's not a lot of flow batteries out there. Flow batteries are large, expensive, but low cycle cost because of very long life batteries, and they're still figuring them out. But they'll probably be good for utility baseload power down the road. We have a couple of different classifications of battery systems. We have self-contained systems, which is like the Tesla Powerwall. It just comes in one package. Then we have pre-engineered systems of matched components. So these are like when there might be a different battery inverter manufacturer and a different battery, maybe a different solar inverter component manufacturer, and they all team up to use each other's components and sell you a system that is similar to as if it was coming from one manufacturer, but there's a couple of different companies involved, like a joint venture product of sorts. This is pretty common. There's a lot of alliances in this industry. And then other. And so other is going to be when you're building your own battery banks and piecing together the equipment and conductors and tools yourself, rather than buying, a listed assembly product. So we have some additional labeling requirements, which were actually new to me. We got the voltage, short circuit current, and average clearing time, and the date the calculation was performed, or if there's some arc flash labeling. And I don't really know much about the arc flash labels, but what this is saying is, look, you need to make it apparent to people that when you turn a battery disconnect off, that voltage in coming off of the battery inverter may take some time to de-energize and drain off to ground. And there's like rapid shutdown rules about how quickly this voltage needs to clear. Generally, it needs to drop down to less than 50 volts within a minute. And so it's more of a issue when you get into higher voltage beyond 48 volt battery banks. But it needs to have what basically is, you can flip the disconnect switch on the AC side and put a voltmeter on the inverter output and see how quickly it drains the ground. We have another rule for partitions when the battery cables, let's say you have the batteries in their own battery room, and then you have all the operating equipment on the other side of the battery room. Maybe that battery box is outside the building and you've located everything inside the building. When the terminals are more than 5 feet from connected equipment, or where the terminals pass through the wall, there has to be a disconnect on the battery side of the circuit. Actually, that's not really a new rule. We've already seen a rule that says, if the conductor cables coming off the battery are greater than 5 feet, then you need to put a disconnect at the battery. And says we recommend using fused multi-pole disconnects of appropriate amperage. So what this is my recommendation, and I found in a note they kind of mention fused multi-pole disconnects, but really you're for disconnecting these batteries, especially with 48 volt batteries, you get into low voltage, high amperage devices, and things like disconnect switches and even the fuses and breakers themselves can start to get real pricey. I haven't found really a better way to beat getting a multi-pole disconnect switch. So you have to be a little bit careful, because if you buy a disconnect switch, it may just disconnect leg 1 and leg 2 and not the neutral. If you buy a multi-pole disconnect switch that has 3 poles to disconnect for leg 1, leg 2, and a neutral, You don't have to use the neutral pole, but it's there if you decide, no, I do want my battery inverter to be completely isolated from the grid. Um, maybe the utility requires it to be completely isolated from the grid. And then a second disconnecting means located at the equipment end when the disconnecting means is not in sight. What this means is, look, you got to have a disconnect at the battery. If it's more than 5 feet away, you have to have a disconnect on the other side where the equipment is, so that you can isolate the equipment from the circuit so that you can work on it. So it's not as simple as just bringing the circuits out to the battery equipment. If they get far enough apart, if there's a wall in between, you gotta partition it. These disconnects are allowed to be in the battery enclosure themselves, in the battery room itself. But if they are, and it's like an unsealed battery, it needs to be listed for a hazardous location. So you're using kind of industrial, NEMA 3R outdoor rated, industrial disconnects or service panels that are anodized. And then we see yet again another requirement to say you have to label where the disconnects are located. So a great way to remember this is on whatever project you are on, you need to have a plaque that indicates where all the disconnect switches are. And you may need to have multiple plaques for that, for the indoor equipment and the outdoor equipment. And just wherever you're at, on these energy systems, you put a map that says these are where the disconnect switches are. Then you'll fly through inspection. Um, okay, so this is another rule that I found pretty, this is a good gotcha. I can see this one easily being messed up. So on a disconnect switch itself, the top of the disconnect switch, so here's our utility conductors coming in, the physically the top side of the switch is harder to access than the bottom side of the switch. These things might have a cover that swings upward, and that cover kind of prevents you from getting into the top of the switch, whereas the bottom of the switch is just hanging out and saying, hey, how are you doing? I'm right here. Stick your hand in me and touch me. Lean into the box and touch these terminals. The bottom side of the switch is easier to touch than the top side of the switch. In fact, linemen, power companies, they're opening this disconnect switch and they're like, hey, I know how a disconnect switch works. And, there's usually something that's connecting these terminals. And by moving the lever, I'm raising that connector up. And now the top of the terminals are still energized and the bottom of the terminals are not. And that's the good rule of thumb that says, I don't know if it's the utility side or the solar side. I don't know if it's the utility side or the battery side, but which side does come in to the top of these terminals? The answer is the side that is actually always hot goes into the top of the terminal, and the side that's not always hot goes into the bottom side. So solar connecting to the grid, the grid will come into the side that's always hot, and solar will go into the side that's always, de-energized when the grid is down. So the question is, well, what about batteries? What they're saying is with the DC side of the battery that's going from the battery, into the inverter, even though the inverter's coming in from the grid side, on this disconnect switch, the battery goes into the grid side and the DC run to the inverter goes on the load side. And instead of memorizing code and trying to say, well, how do I, for every single technology, they have all these different rules. It's like, no, actually, the top side of these terminals is always hot. And since the battery is always on, we want the top side to be considered the hot side. So here in code, it's saying the battery terminals are connected to the supply side. And there you go. Now, I've made a mistake before on a job where we have the disconnect switch on the wall, we have the solar array coming down from the roof, and we got the grid coming in from underground. And so we went and we landed the grid underground, and we landed the solar array on top, thinking, oh, we're making things nice and simplified by not looping our wires around in this box. And that was ignorant of, no, when you're servicing inside this box, if you feed the grid in from underground, then the most accessible side of that box is always energized. And that's a safety hazard. You can't work in the top of the box with the bottom of the box being energized like that. But vice versa, a competent, qualified electrician, who understands what he's doing and has done a good job with quality workmanship, they can work in the top of that box. In the bottom of the box with the top being energized. All right, so we get back into some requirements that we saw in earlier parts of code. So we get into ventilation requirements. We have another, reminder that live parts need to be guarded against, whether it be a dedicated room with a lock on the door or a wire, physical barrier preventing people from being able to fall in or touch the batteries. We say, okay, well, if you are building your own battery, so if you're not using a Tesla Powerwall, if you're not using a pre-engineered or self-contained system, where an inverter company, a battery company has got together and says, here's our battery cabinet, buy all this, assemble it this way, this is our system. If it's not a pre-engineered system, if it's not a self-contained Tesla Powerwall system, you have further constraints about what you can do to be code compliant. So a Tesla Powerwall could go right onto the wall of a garage. If you're building your own battery cabinet and buying lithium-ion batteries and assembling your own battery bank, there has to be a 1-inch clearance between the batteries and the wall. And then there's this weird special case that says, well, actually, we'll let you put the actual rack up against the wall as long as you take 10% of the long end, the length of the shelf. And if 10% of that is the distance between the battery and the wall, then you'll be fine if the shelves are flush up against the wall. I guess that's for the obsessive compulsives who can't have their battery rack be exactly 1 inch from the wall. Or perhaps if you're building the shelves out of the wall themselves, there's a clearance requirement that says if your battery trays and supports are touching the wall, then there's this special exception. We again see the means of egress requirement, the need for illumination requirement, so we're not going to spend more time on that. The conductor ampacity is it should not be less than the nameplate current rating of the inverter system or the overcurrent protection device protecting the system. And so this is where I've seen a design mistake where they look at the battery and they say, okay, well, this is the battery supplier said this is a 25 amp battery, and it was a homemade battery. He knew it was 25 amps, but it's not like this was a do-it-yourself project, and the guy had bought this battery and had a 25 amp wire going up to it. Well, then he goes and buys a 12 kilowatt battery inverter because he sold a system that was supposed to do whole house backup power, and he needed a large inverter to do that. Well, the problem is this was a 48 volt, battery. And so if we have 12,000 watts and we divide by 48, volts, what we're getting up to is 300 amps. And so, he sized this conductor based off the amperage. The battery supplier supplied the conductor based off the maximum ampacity of this battery. But really, the fault of this particular system is, they needed to buy not just 25 amps worth, but they needed to buy, oh geez, a good 12 times as many batteries to parallel these batteries enough, to get up to a true whole house power system. Otherwise, his 12 kilowatt inverter would have pulled out, would have tried to pull 300 amps out of this 25 amp battery. And so if the system had been installed, it would have burnt the house down. So you really have to be particularly careful because, with high voltage, low amperage lithium ion, if you're trying to do it yourself and you put it on too large of an inverter, you have to be aware of that lower limit. In the battery classes, we talk about this in terms of there being a minimum battery size, and that's kind of based off the size of the battery relative to how quickly you could discharge it based off the inverter that you connect it to. So we see the overcurrent protection device should be not less than 125% of the maximum circuits. Particularly with the batteries being able to surge a little bit and the inverters being able to surge a bit, not for minutes but for seconds. You don't want to you want to make sure you use that full extra 25% range on these heavier amperage systems. Sometimes, that 300 amp, you oversize it by 25%. It means you have to get up to a 350 amp specialty breaker. On the DC side of these things with the low voltage, high amperage products, it starts to be very difficult to find a DC breaker that's rated for, 25% larger than a whole house low voltage, high amperage battery. I mean, what I have gotten to the point where, I buy the breakers from the solar vendors and then I look up what the original equipment manufacturer of the breaker is and try and research that supply chain, because the solar guys charge, $100, $200 a breaker. But ultimately it's because they don't make very many 60 volt DC, 300, 400 amp DC breakers. You go into Home Depot, you go and you look at the breakers on the shelves, they only get up to 30, 40 amps. You have to start going to a supply house and going to the big boy supply chain to get, heavy amperage breakers, and they're not made as often. They're more expensive. Fast forwarding a bit, dwelling units, batteries are not permitted to be over 100 volts unless the live parts are not accessible during routine maintenance. Okay, well, most sealed batteries do not need routine maintenance, so that's really not an issue anymore. Sealed lithium ion is allowed at higher voltages. When you're doing maintenance on batteries that are sealed, if you wanted to, it's not done commonly, but if you wanted to wire up like some high voltage lead acid batteries, you would need to be able to isolate them into a maximum of 240 volt segments to perform safe maintenance on them. And I would want it to be a lot less than that, to tell you the truth. That's breaking out your gloves, insulated tools. Anything over 100 volts needs a maintenance disconnect for fully isolating the battery from the system, including your neutral conductors, or the battery negatively grounded conductor. So anything over 100 volts on your battery bank, you're going to need to have disconnects for both the positive and negative side of your battery anyway. So for that matter, getting a heavy duty unfused disconnect switch and then having a box that has a fuse block and fuses, or just going ahead and getting the fuse disconnect to begin with, can be an added cost of doing it yourself, as opposed to getting an integrated system uh, that has all these switches presumably built in. Floating batteries are allowed. That's you fuse both sides of the battery and don't connect any to ground. It says flexible cables, finely stranded cables are capable, are allowed within the battery enclosure. That can make wiring the battery much easier, especially with like forklift batteries, where you keep the wiring inside the battery and kind of lay it into the case of the container that the battery comes in. Has some clearance for you laying down the battery cables around within the battery enclosure. It says you can do that with flexible cable within the battery itself. You still have to oversize by 25%. Now we're going to get into the solar section, but the last sections of code that you might want to look into are requirements for off-grid standalone systems. You might have to put in an extra ground, like a supplementary ground rod. And then there's even additional sections for direct current microgrids. Another section that's worth looking into is communication systems. It's gotten a lot of revision, and the main thing that I would say is there's such a thing as direct burial shielded Ethernet cable, and even if they're allowed to be in the same conduit as your solar conductors, it's they do better and sometimes have to be isolated from the solar conductors, particularly with like utility scale systems where you're digging a trench. The fiber optic cables would go substantially above the power cables down in that trench. Before we get into the solar section, there is a section on electric vehicle storage batteries that say, in your electric vehicle charging stations, they need to be in ventilated rooms based on cubic feet for ventilation requirements. I don't think I translated that chart exactly right, but basically the heavier duty the battery charger, the better. Some of these electric vehicle battery chargers, I was looking at one the other day that was like 400 kilowatts. Dear Lord, they're like, I guess, when your battery is 100 kilowatt hours, you can get into commercial, vehicle chargers that, 100 kilowatt charger with a 100 kilowatt hour battery, it would take an hour to charge up your electric vehicle. And that's if the battery can take it. Not a different. Anyway, incredibly large DC chargers in the EV space. I like to think about how to cost effectively build a do-it-yourself system out of common parts that might be cheaper than using the proprietary listed stuff. And it's hard to do it in a code compliant manner, but if you had a DC electric vehicle charger charging up a homemade higher voltage lithium ion battery pack, you could connect it to the DC side of a solar inverter, and provided that you had intelligent controls, you could turn that inverter on and off and just dump whatever battery power into it. So particularly in the commercial solar peaker class, you can look into code and say, look, there's ways that we could put high voltage electric vehicle charger on a shipping container worth of DC batteries, and then have a series of just cheap old solar inverters coming off of it, and provide low cost battery peaker systems for demand management that sit outside the building, still have it be done in a almost all the way listed manner. I say almost all the way because your local jurisdiction really at this time would still have to sign off on used lithium ion. Let's talk about solar. Um, they say the solar system has to be functionally grounded. That means that it needs all the grounding electrode, equipment grounding conductor. It can be a floating system, or older school systems would be negatively grounded. Most solar inverters today are floating. They don't negatively ground the system. They have inline overcurrent protection on both the positive and negative, disconnects on both the positive and negative. The generating capacity of the system is the inverter output. That's typically rated at 40 C in kilowatts. Maximum system voltage. One or two family dwellings cannot have circuits above 600 volts in the US. Other countries, they allow up to 1,000 volts. Other countries, that can make electrical wiring a little bit cheaper than in the US. But, our code is very conservative in many circumstances. Not all circumstances. It's not rigid. On other kinds of buildings, you can have more than that. On utility scale ground mounts, you can have 1,500 volts. If you're building a ground mount at a residential level and you have a detached equipment building for your solar inverters and electronics, you could still do a 1,500 volt system. There are more requirements for higher voltages. Putting a fence around the solar array. Even with a ground mount system, you still need to protect the solar array from just people walking up to it. Let's see. There's for voltage, it used to be that we would take the system voltage and then have some fudge factors to be applied to it. Now it's saying for the voltage ratings, you need to take the 100% voltage rating, maximum open circuit voltage, and then go through the process of correcting the voltage for temperature extremes. In our solar class, we talk about a temperature coefficient of power. You multiply that by the temperature differential to adjust the module voltage. There's a table right in code that'll allow you to do that without knowing the module spec sheet, and that's because the temperature impacts on traditional silicon solar panels are very close together. The difference between a quality solar panel and a lower shelf, almost bottom shelf solar panel in terms of temperature heat loss, it's within 30-40%. It's not a 100, 200, 300% difference. So this correction factor is conservative, but the table's right there. You don't need to pull up the module spec sheets to do your voltage calculations. But you look at your coldest expected ambient temperature, which you can find online, and apply the correction factor towards your open circuit system operating voltage. And then when you get into larger systems, an engineer could say, actually, the coldest ambient operating temperature in this area is at 3 a.m. at night and gets down to -20. But by the time the solar array turns on at 8 a.m. or 9:30 on that winter day, it's going to be up to -10 instead of -20. So I'm going to sign off on that, and that'll let you get a little bit lower voltage range. But that usually doesn't matter. I mean, the voltage is going to determine how many solar panels you can fit on a given circuit. So sometimes that difference between fitting 14 panels on a circuit versus 15 panels on a circuit can have a tremendous impact on a utility scale project. Not a huge difference on residential. I like designing up to the maximum voltage on a system, but I just pull open the string sizing software and let that tell me what it is. Let's see. Well, then we have, so these rules governing maximum voltage. It's just saying use the listed output of the system. Don't apply an additional 25%. Just use the listed output of the system and then use the temperature correction factors to get your maximum voltage. So you look at your module spec sheet and it says it's 50 volts, and then you look at the temperature correction factor and it says, okay, well, at the coldest time of the year, the module voltage could get up to 60 volts. You have a 600 voltage upper limit. You can fit 10 of those panels on a circuit. So determining how many panels can go on a circuit, determining how many panels will get you up to just under the maximum voltage range, you got to take the module voltage and then adjust by temperature. Voltage is like the skin of a water balloon, just a little bit more than what it's capable of. It can pop the microchips in the equipment and brick the system. So you don't ever, amperage, if you go over amperage for a short period of time, the wire heats up. It takes a longer period of time for the wire to begin to smolder. So current's a little more time delayed, a little bit more having to do with flow. Voltage is more instantaneous. It more has to do with the pressure. A little bit too much pressure causes the water balloon to burst. Stress versus strain. Now, ampacity is different. Ampacity is, normally for a National Electric Code, you take the current rating of the circuit and you add 25%, and then you size the circuit conductors based off of that. Except solar, the voltage generally climbs a lot faster than the amperage. So to that respect, the voltage, even though it climbs faster and it's more volatile in terms of runtime hours, voltage is going to be more stable and amperage is what's going to be going up and down. If there's no clouds in the sky, at 9 a.m., the system voltage is going to start climbing and then reach its maximum by 10 a.m. And then the voltage is going to be more steady throughout the day at high noon, at 10 a.m., at 3 p.m. And it's the amperage that's going to ramp up and down. So voltage is very much impacted by temperature. Amperage is a little bit impacted by temperature. We have these voltage temperature correction factors in code, but code is looking at the solar panel spec sheet is done at a 60 degree Fahrenheit module temperature, and most rooftops are substantially hotter than that in the summertime. Voltage goes up in the wintertime, amperage goes up in the summertime. So how do we, solar is headed for a special case because it's in an extreme temperature and its spec sheet is rated at a lower temperature than what the operatings are. And we saw in our earlier general code class, if things are rated at lower temperatures, the temperature correction factors applied to them are harsher. Solar, we're in this specialty case and it says, look, if you are calculating the ampacity of these conductors, you need to take what you would normally calculate at, which is the output ampacity of the inverter times 25%, or the output ampacity of the modules times 25%. The normal rule of thumb for electrical is you take the output current of the device and multiply by 25%. And it says, but solar is special. For if you have a combiner box that's rated 200 amps and you have individual circuits that are rated 8 amps each, and you're trying to determine how many solar circuits go into a combiner box, on a service panel on the AC side, you'd say, okay, well, what are all these devices doing? And then 25% more than that, and then we haven't overloaded our bus bar. On an in-phase microinverter circuit, we say all these microinverters are 16 amps each, and then we multiply by 25%, and that gives you a 20 amp breaker. On the DC side to solar, on the output of the solar panel itself, that output is rated at the standard test condition and not at the higher temperature extreme where amperage increases slightly. So we have to account for that. And we're not applying any temperature correction factors for amperage. So what gives? Well, here it is. Normally you would take that module output amperage and multiply by 25%. And right after that, it says, well, for sizing solar conductor ampacities, you need to apply an additional 25% to make sure that ampacity is oversized. And then you can also go and look at other correction factors, the distance from the roof, the number of conductor cables in a conduit, and apply all those corrections, which are part of the general parts of code. And you use the greater of the two. So it's saying use the greater of, adjusting for all the ampacity and correction factors, or 25% beyond the initial 25%. So most solar calculations for dumb circuits that don't have anything smart going on, you take the output ampacity of the solar panel and you multiply by 25%, and then you multiply by another 25% because solar is special, and that gives you the design amperage. So your 9 amp circuit, all of a sudden becomes a 15 amp effective design constraint. And so on a 200 amp service panel, you can only fit, 17, 18 of those circuits into a 200 amp panel, combiner panel. But then there's an exception. It says, well, that was how it used to be when you just had different, solar arrays, subarrays, and all their circuit conductors come into one point called a combiner box, and then we have one output from the combiner box back to the inverter on the side of the building. Well, nowadays it's we have all these module level controls, within the array itself, doing all sorts of shade mitigation and voltage correction. And code now says, well, if you're using electronic overcurrent protection already in the circuit, then you don't need to worry about this oversizing, because these boxes are detecting when you get into an over amperage situation and then scaling back the production. So in reality, we're already using oversized conductors in the solar industry because of voltage drop, because these devices are a very long ways away from where they're being plugged into. And so even though the amperage over constraint for solar in the absence of microinverters is pretty harsh, the temperature constraints are even harsher, and then you still might upsize your cable beyond that because of voltage drop. So it's not a situation where you're paying more than you have to because of amperage oversizing rules. Let's see. So this is saying overcurrent devices are not required on solar circuits where you only have one solar circuit and not any other parallel circuit. So we saw that in the battery situation too. When you have two or more power sources being combined together, you need to make sure there's overcurrent protection somewhere in the line. Either at that point where they're being wired together in terms of breakers onto a service panel, or at the device itself on their own fuse disconnect switches. But there needs to be overcurrent protection. There's an arc fault protection requirement for solar arrays. except for solar systems that are not installed in or on buildings. So this is arc fault detection is more expensive. It's relatively new, although most inverters, grid tied inverters, have arc fault detection now. You can get cheaper battery inverters that don't have, cheaper solar inverters that don't have arc fault protection built in, and you're not going to be able to go find arc fault detection breakers very cheaply. And so there are lower end solar components that, to be code compliant, are only suitable for ground mounted projects. So now we get into rapid shutdown. This actually comes a little bit later. It's 54, not 12. I must have mislabeled that. But, basically rapid shutdown has allowed different rules in the past. And today you have to limit, it says, the controlled conductors inside the boundary of the array, or within 3 feet from the point of penetration. Where this is coming to is, it says in the past they haven't regulated the inside of the solar array boundary, but now they are. Then there's field labeling requirements, and basically because there's been systems that have had different standards of rapid shutdown, which requires you de-energize the array upon command. In the past, it's applied to a 6-foot perimeter. Then it applied to a 1-foot perimeter, but just outside the array boundary. Now they're saying, no, we want to shut down the high voltage circuits that are inside the array boundary too. And so now that field label needs to explain which kind of rapid shutdown compliance the system is actually compliant with, so that when the fire department pulls up, they see that it's a solar array, they can read that it's a rapid shutdown system. Well, they still need to know what kind of rapid shutdown. Is it based off NEC 2014, 2008, 14, 17, or 20? And they say, well, rapid shutdown doesn't apply to solar arrays that don't have any exposed or conductive parts, like maybe solar shingles. I think that's going to change. We're going to wrap up real quick here, but there's a 6-handle rule, this common quiz question. If you have 6 or more solar inverters wired into one service panel, the 6-handle rule applies. More than 6, you got to have a main switch that disconnects all the systems at once. Just like a main breaker on a main service panel has the 6-handle rule, it comes back in solar as well. It says equipment that performs rapid shutdown functions other than the initiation devices should be listed for providing rapid shutdown protection. So I have a smart wireless controller that I can press a button and it sends a relay signal to the inverter. The inverter has a input relay that says I'm a rapid shutdown inverter. So my little initiation button does not need to be listed. That's actually pretty interesting. So sometimes the initiation button can be that accessible service disconnect, or that readily accessible disconnect. It does not have to be the readily accessible disconnect. It can be an additional, push button disconnect. It says, this is my rapid shutdown initiation system. And even the push button itself does not need to be a listed device. The rest of the system needs to be a listed device. The solar disconnecting means, though, there still needs to be a readily accessible disconnect, appropriately labeled, follows the 6-handle rule for simultaneous disconnections of the load. And then lastly, that disconnect needs to mark what side is the load and what side is the line, because that's not so obvious to a lay person. Didn't really want to run over time. Combiner boxes now need disconnects if the combiner boxes are over 30 amps. So they need to be isolated from the array. Generally, combiner boxes on smaller systems, residential systems, commercial systems too, have kind of fallen out of style. The inverters themselves are now doing the combining inside the inverter. So you just pull all of the solar circuits, in their uncombined small conductors back into the inverter itself more commonly. Um, let's see. You have to group AC circuits separately from DC. Now, how you do that, you can just use zip ties and bundle them separately. PV wire and USC2 wire are both approved for outside of conduit use up on the rooftop in a solar array. Other cables that are outdoor rated, wet environment rated, are also approved, but they may need to be only used in conduit. So often you're using the outside of the conduit, transitioning into a box, and then using your inside of conduit from that point forward. When DC circuits go into, sorry for running over. I need to speed up a little bit, but we'll be done in a minute or two. DC circuits inside of buildings need to be in metal conduit. So as soon as you go inside that building to the first access point, it needs to be in metal. I like using MC cable, but if that MC cable gets too small, it is required to have additional physical protection. So I use MC cable that's over 1 inch diameter with bigger, thicker, number 6 cable. If you were to use number 10 MC cable for a single circuit, it might not work out so well. Solar labels should have capitalized lettering. DC circuits throughout the house need to be labeled every 10 feet. So you get tons of solar caution, photovoltaic output circuit stickers to wrap around your conduit as you're going from the array back to the inverter. You are allowed to put junction boxes underneath the solar array, and that's specifically referenced in code. Though even though the panel, you have to use a tool to take the panel off, and then you have to use another tool to take the lid off. Let's say that's allowed. I like putting my roof mounted equipment underneath the array. You have to be careful that you have the clearance to do it. That usually requires a specialty box, but it shades and protects the boxes. It's best for it. So here we have stuff that we've already seen in code before. The minimum equipment grounding conductor, if it's smaller than number 6, it needs to be in conduit. That's no problem. MC cable has a protection, for that. The equipment ground conductor for the solar array has to be in the same raceway as the PV circuit when it's leaving the vicinity of the array. So there's not just the grounding electrode conductor, there's the equipment ground. The grounding electrode conductor for DC, bare number 6 up to the rooftop, can be outside of that conduit. You still need a ground continuously wound with the rest of the system. That's the equipment ground. I usually combine the two together. I upsize my equipment ground conductor so that it also serves as the DC grounding electrode conductor, and that's why I upsize my MC cable. Let's see. So finally, we get towards the end of this section. We have standalone equipment needs to be identified. Utility interactive equipment needs to be identified. And the rapid shutdown explanation. How is this? What does this system use to do rapid shutdown? All need to be labeled on the side of the building. So I don't really think about these labeling requirements as this, and this. It's more of every time there's a deviation from standard, you need a sticker that says this thing is different. Polarity of systems going into batteries need to be marked, and then that's the end of the program.